It's a little bit embarrassing as a scientist to have people pay $8 to hear you talk. But Dr. Peach reminded me that you were actually paying for the refreshments. So with that, let me tell my second joke of the evening. These are some La Jollans with their real estate agent. And this cartoon, it's amazing how the cartoonists, including Jim Barry, this came out during the 1982-83 winter, when literally all hell broke loose. Can I say that on TV? And El Nino became a household word. There was lots of erosion and lots of storm damage on the coast. But in the last 40 or 50 years, you would think that this was literally true, given the population pressure, the development pressure, the rebuilding, especially in desirable places like La Jolla, but in all of Southern California in general. You would think that this was literally true, that people were trying to buy up and improve this property faster than it could erode away. Now, having started with a little bit of levity, I'm going to end, let me just anticipate this, I'm going to end on a much more somber note, because frankly I am not very optimistic about the future of California's beaches, and I'll tell you why. First of all, the future of beaches in California is not only related to the future of sea level rise and the rates of sea level rise, but it's also critically dependent, and we know this from the historical record, it's also critically dependent on the sand supply as well as the wave climate. So climate and weather impacts, especially through the waves and especially through the alterations in runoff and changes in runoff, bringing sand to the coast through the rivers and cliff erosion, play into the future of and will determine the future of the existence and the width and the condition of California's beaches over the next century, as much or more than the actual projected sea level rise. Now, sand supply, of course, as I said, is dependent on climate. And it's also, even more importantly, as far as the past is concerned, dependent on human development and sand supply brought to the coast by people through various means. So we'll talk about all that, and I'll present all of that in illustrated form as we go along. So, as a general background theme or themes, I've listed here my view of what the major beach issues are in the next decades and century. The first is getting and keeping enough sand on the beaches to satisfy the recreational tourist demand, to reap the economic, habitat, cultural benefits that come with it, with the beach culture, and with wide and healthy beaches. And also to provide some property protection, although most beaches will never be wide enough, we'll see this in Southern California, to provide protection during all possible events. And the second point, and this is closely related, is finding and maintaining the appropriate balance between sand supply, sand retention, armoring, retreat, that the continued erosion, if it occurs, may require and may make necessary. This is essentially not a technical question. The technical aspects of the second part of this are much advanced compared to the social, political, legal, economic issues that are involved in finding and maintaining this balance. And of course, as you know and as you might expect, different interest groups and different constituencies will have different views about what that proper balance should be. Now, talk about the cultural value of California beaches. Baywatch, for whatever purpose, I certainly can't figure out why it might be. I'm sure it's because of Mitch Buchanan over here, or maybe because of the swimsuits. It's the most popular TV program in the world. So this illustrates that beaches are the essence of California. When the first thing you think about when someone says California, the first thing most people think about are not the freeways or the mountains, it's the beaches. The whole surfing culture, shown here with this album cover from the Beach Boys, and of course the massive industry involved in surfing that's developed around the California surf culture is a huge economic engine and a huge cultural value. And of course, there's nothing more culturally interesting than a day at the Venice, at the Venice Zoo up there in southern LA. Now, let me get a little bit more serious. You've probably all heard these statistics. I can never remember all of these numbers, but 50% of the people live within 50 kilometers of the coast or 50 miles or whatever it is. So you have all of these economic statistics and all of these, people population statistics and all of this stuff. I've just pulled two of them out here at random that illustrate the enormous amount of money involved in the coastal economy. $3 billion in expenditures was estimated per year, hundreds of millions of visitors. This was a UCLA study. The Department of Boating and Waterways, that's the agency I work for, estimated $27 billion in economic impact. And you have to ask an economist, to tell you what the exact differences are between expenditures and total economic impact. Anyway, these numbers are in the billions. They're large. The tax revenues associated with coastal tourism is very large. There's 5 or 6 billion a year, billion with a B, in state taxes alone. Of course, the ecological value, I mentioned the cultural value. Beaches provide habitat, they provide foraging space. It doesn't mean foraging for rare and endangered birds, it means foraging for, you're not supposed to shoot them. The rare endangered species, do the foraging, you might understand. All right, in fauna, those are invertebrates that live in the sand. That's an important thing. Grunion, of course, is another quintessential California activity. Now, this is in conflict, somewhat in conflict. The sandy intertidal and sandy beach habitat is somewhat in conflict, and this comes up during beach nourishment activity. With the hard bottom and inter and subtidal habitat that also has enormous, and in fact some would argue more value, especially the high relief habitat is good for lobster and kelp and all of the nice ecological niches that you see off of La Jolla and off of Point Loma, for example. No beaches involved, it's purely rocky intertidal and subtidal, so there's some tension between the ecological value here between beaches and the other rocky habitats. Now, I mentioned I'm going to talk about all of this in the context of coastal processes. The important coastal processes for these purposes are these 6. First of all, the geological setting, which is fundamental to everything, and I'll talk a little bit about that in a few slides. The sand supply, which is fundamental to everything, and I'll talk about that in a few slides. And then there's the waves, which is fundamental to everything, as I've said, and I'll show a few slides about that. And then the climate, which is next, and the tides and sea level, which is in some sense secondary to these first 3. And then, of course, human influence, which is also fundamental, as I've said, and I'll have a few slides and sort of spread through the whole thing. You'll see if you can see these threads of human influence through the whole discussion. Now, where are we? Well, we're here somewhere, California, Southern California in particular. You'll see these red dots are volcanoes. We don't have any volcanoes in the immediate vicinity, goodness gracious. But we are on this thing that's been called the Pacific Ring of Fire. And what that is the boundary of the Pacific Plate, and particularly the boundary of the Pacific Plate where it previously, or in some places, still collides with the North American Plate. And over the last 20 million years or so, we are along this so-called transform fault, so we don't actually have a lot of up and down movement because of this tectonic activity, as opposed to most of the rest of this plate boundary. But we do have a lot of lateral shifting, and I'll show you in a minute. Even the lateral shifting does lead to some ups and downs, like, for example, Mount Soledad, that are important to the coastal setting. So the same geological processes that form the coast that lead to these disasters, like the 1906 San Francisco earthquake, the 1989 Loma Prieta event, and of course the Christmas, 2004 or 2005 event in Indonesia that caused all of that damage that everybody saw, and tidal waves and all of this devastation. All of these same processes are related and are fundamental to why the California coast looks the way it does. And so that at least that remnant collision coast geology leads to what the California coast looks like in the fundamental coastal setting. So a little bit closer look. I love PowerPoint because you can do all this cool stuff with sea level rise coming up out of the bottom and tectonic uplift. I didn't make them go different speeds. The tectonic uplift around here is a factor of 20 or so smaller than the sea level rise. So except for the features I'll tell you about in a minute, that's not really crucial to the beach setting. Anyway, as I said, the fault system here, the San Andreas fault system, is not just the San Andreas, it's a whole series of faults, including our local one here, Newport Inglewood Rose Canyon fault. And these faults, these are not my faults, these faults are these faults are not, it's a tough audience. These faults are sinuous, they're not completely straight, and the fact that they're sinuous, in other words, they're S-shaped, they're curved, and this right lateral motion, now this is really confusing, they don't want me to walk in front of the screen, but this is, I've never quite figured out how this works. If you stand here and look at the North America plate, it's moving to the right, that's why it's called right lateral. And if you stand on the Americas plate and look to the Pacific, it's also moving to the right. Someday somebody can explain how exactly that works. But there you are, it's called right lateral. So the southern part, the western edge of California is moving north relative to the rest of North America. And because of the sinuous nature of these faults, these blocks can't slide past each other smoothly, and parts of it have to go up and parts of it have to go down because they end up, because of the S shape. So this leads to these alternating highs and lows. The hills of Tijuana, for example, the low is the San Diego Bay, the high is Point Loma, the next low is Mission Bay, and the next high is Point La Jolla, and the next low is, well, it's up at Torrey Pines somewhere, not as obvious. So and it also leads to these other, directly leads to these other headlands, Palos Verdes, for example, Point Conception, that's a little bit different. This whole block is rotated, it's a different story. But anyway, the coastal geography of the California coast is essentially dominated and looks the way it does because of this geological setting. So what does this do? Well, because of the young nature of the coast, it's active, steep, and therefore it's eroding. And with this slide on the bottom here, thanks to Doug Inman who produced this slide. Doug is in the audience, by the way. And I should mention that many of the concepts that I'm talking about were developed by him and originated by him, and many of the illustrations I'm going to use were also originated by him. So thankfully he's here because he can answer all the hard questions later after I'm done. All right. What this means for the immediate shoreline is that because it's young, there's relative scarcity of sediment compared to, example, for the East Coast, which age is measured in hundreds of millions of years compared to our coast measured in tens of millions at the most. And what that means is that there's a thin, relatively thin veneer of sediment, beaches, that is, sand beaches, over a bedrock platform that's been cut over the last 6,000 years or so, and we'll get into that in a minute. What's shown in this illustration is the sea cliff line today, which is here, and the sea cliff line about 6,000 years ago when sea level, the rate of sea level rise slowed for the last time since the last ice age. And so sea level rise has been relatively steady in geological terms. It only rose, say, 4 or 5 meters or so over the last 6,000 years. However, the retreat here of these cliffs was between 500 and 600 meters, so it's half a kilometer, quarter mile, a little more than a quarter mile or so, from where the shoreline was 6,000 years ago out here to where it is today, because directly related to sea level rise and then this coastal erosion. So this is what we get for this beautiful, high relief, relatively, geologically speaking, relatively young coast. It's eroding, it's naturally eroding. All right, now let me talk a little bit about sand supply, and this sequence starts down here at the lower left by this nice aerial photo of Doug's from a typical quintessential Southern California. This is actually Baja, but a Southern California river that has a lot of sand in it, but no water most of the year. So the picture here is that sand erodes off the hills, it gets into the rivers, and then during flash floods when it rains, and then a bunch of sand comes down to the beach and forms a delta. The waves then act on this sand and distribute it along the coast. So that's the kind of classic picture of sand coming down the rivers toward the coast. Now, over the last almost 100 years, I suppose, since at least the 1930s. We've built flood control and water storage, reservoir, dams, all up and down, literally hundreds, if not thousands of these things in California. Every major drainage has some kind of flood control or water storage dam on it, including all of the rivers in Southern California. And this has cut the natural supply of sand from rivers in Southern California by about half. So cliffs also contribute sand through superficial erosion, through rilling, through landslides. Here you see a nice picture of a landslide. It's at San Onofre, and also by these large gullies, some of which actually extend all the way back to I-5, which is right here. And also the same kinds of processes, not so much these large barrancas, but the same sort of processes, landslides, superficial erosion, and rilling and gullying from Torrey pines. And I want to point out that, of course, as we proliferate seawalls, and I'll talk a little more about seawalls and the seawall debate as we go along, as we build seawalls to protect our coastal property and our coastal infrastructure, the amount of sand from cliff erosion will decrease and will continue to decrease at an accelerated rate. Now, I use this slide, a picture of Scripps. You'll recognize the pier there. There's the marine biology building. There's some nice cliffs that are protected. The entire frontage of Scripps is, of course, fronted by a seawall. So it's not just these rich, old fogies living on the cliff top in Solana Beach or in La Jolla or in Encinitas, wherever. There's also a whole host of public infrastructure. Arguably, this is an important place. Geez, my office is right there underneath. It's right on that second floor, right there. So, 6 meters of sea level rise, and I'm going to need floaties. I'm going to need swimming aids. The point here is that seawalls also protect much public access, including public parks, beaches, parking lots, access, state parks, structures of all sorts, et cetera, as well as the rich old fogies. And can I say that on TV? In Solana Beach. I apologize to my friends in Solana Beach ahead of time if you see this. All right. Let me get into the beaches and littoral cells a little bit. This is another real nice picture from Doug's collection. And it shows the bedrock platform down here, and it shows typical summer beach configurations in cross-section. There's some nice pictures of waves. The idea here is that during the summer months, the waves are relatively small. They push sand up from offshore. They push sand up to form the beach. In the wintertime, the waves get bigger on average, and then they take that part of that sand that's up here on the upper part of the beach and move it offshore into this area. And this occurs out to 10 or 15 meter depth or so on a regular, normal basis. Now, I want you to look at these wave heights, but try to remember these numbers here. The amount of sand moved roughly for 1, 2, and 4 meter wave heights ranges upwards of 500 cubic meters per meter. What this means is, for every meter of beach length, in other words, if you walk on the beach, I'm not going to get out of the picture, don't worry. If you walk on the beach, for every meter of beach that you walk, the seasonal changes in sand volume amount to 500 to 16 or 1,800 or so cubic meters of sand. So that's how much sand is in motion. This is a big number. If you had to buy this, it's $5 to $10 a cubic meter. Okay, so you can see for each meter of length of beach, and the California coast is 1,000 miles long, you can see how expensive putting the sand that nature moves around for us might be to replace. And that's going to be toward the end of what I'm going to say. These are going to be numbers that I'd like you to keep in mind in the context of how much it's going to cost or how much it may cost to replace the sand that we might lose by drowning due to sea level rise. The other picture down here is also a concept that Professor Inman developed with some others, and this has to do with the geographical compartmentalization. God, English isn't my first language. I apologize for trying to get that out. Anyway, the California coast, and in fact the coasts of the world, can be divided up into these things called littoral cells, L-I-T-T-O-R-A-L, littoral meaning near shore. And they are divided by, again, these headlands. So the headlands, like I said before, these tectonically formed headlands, Dana Point up here and Point La Jolla down here, form the boundaries of the so-called oceanside cell. And of course, we're down here in La Jolla at the southern end of that cell. So the picture here is that sand gets into these cells, waves moves the sand along shore, and then it's lost offshore and through the canyons at the southern end of the cell, and it doesn't go around the headlands. It gets stuck there. So these cells are a conceptual idea of how sand moves, gets to the beach, moves through it, moves through the literal sand system on the California coast, and in fact has application worldwide. Okay, now let me throw some numbers at you. I apologize, this slide's hard to read, but as far as sand supply is concerned, what I've done here is I've plotted the cubic meters per year derived from 3 different sources. That is, rivers under natural conditions if you didn't have dams, rivers under actual conditions with the dams, and then sand nourishment. And what you'll see, except in the Santa Barbara cell, the northernmost one from Point Conception south toward Ventura, except in that cell, the nourishment, the artificial placement of sand is at least equal to, if not much bigger than, like in the Santa Monica cell. These are the Baywatch beaches, of course, right here. You see the nourishment sand amounts to 400, almost 500,000 cubic meters per year for this 50-year period. And it's much, much larger than any kind of natural supply. There's essentially no, since the LA River diverted course in the 1800s, it now comes out south of San Pedro, comes out south of Palos Verdes Peninsula, right behind the Queen Mary, in fact. There's no major river contribution of sand to the Santa Monica cell, and so essentially all of the sand that hits that was produced by large coastal construction works. This includes building the airport, Marina del Rey, dredging out wetlands to create small craft harbors, something we're not want to do anymore because we recognize that wetlands also have value, they're not just swamp and overflow lands like they used to be called, ripe for dredging for small craft harbors and other projects. So these large amounts of sand, same here in Silver Strand, that's another good example. In the Oceanside cell, you see that the total of the nourishment sand plus the actual from the rivers exceeds what used to come the actual from the rivers exceeds what used to come from the rivers naturally. So even though we've lost almost half of the river supply, that's been made up for by nourishment. And that explains, that goes a very long way, if not completely, to explaining how come we haven't lost more beaches in the neighborhood than we would otherwise have. And it certainly explains why Santa Monica and the Silver Strand, from Coronado south to Imperial Beach, have much, much wider beaches than they would naturally have otherwise. So I'll show you some pictures here. While it is true, and this mainly is to emphasize the role of sand retention structures, both natural, like Point Dumais here, you see there's no beach on the south, there's beach on the north. I could have shown Point Loma, same thing. Mission Bay, Mission Beach has sand, Ocean Beach has some sand. You go around to Point Loma, there's no more sand except for pocket beaches until you get over to Coronado. So here's the Hotel Del. All of this westward, or I should say southward, this is a south-facing beach. Southward of about this line here is essentially all built on fill that was dredged from San Diego Bay, moved up here, and is stabilized by this jetty that was built, I think, in the 1940s to try to create a wave shadow here for a small craft, little landing kind of harbor thing. But of course it worked. It did in fact shelter the waves and accreted with sand due to this large supply that came from San Diego Bay right after World War II. It was in the 20 or 30 million cubic meters over that period of time. And that was that large bar in the previous graph. Now in Santa Monica Bay, this is Marina del Rey looking north toward the offshore breakwater in Santa Monica, which is right here. You see the bulge right there. In the 1930s, you can see pictures, turn of the century to the 1930s, you can see pictures where waves are essentially breaking on these bungalows and breaking through the doors sometimes and flooding the streets. And of course now the beach here at Marina del Rey is over 1,000 feet wide. And so this is for two reasons. First of all, the supply that I mentioned, and secondly, the stabilization, the fact that this sand is trapped because of all of these sand retention structures, in this case artificial, not natural. But natural or artificial, they both serve to retain sand. Now this isn't to say This isn't to say that all of these sand retention structures, harbor structures, are good things. Certainly in Oceanside and Santa Barbara, those are two examples. And in fact, in the early days of construction in the 30s in Santa Monica Bay, there was quite a bit of down-coast erosion due to the construction of these. But once these systems are bypassed, this is very much different than the East Coast. On the East Coast, from Florida north to New Jersey, at least 90% of the erosion problem is directly attributable to inlet structures. And you have huge offsets north and south, or depending on which is up coast and down coast. Usually the north is much wider, the south is much narrower. We don't see anything like that on our coast. So again, it's not to say that all structures are good, but it is certainly to say that many structures are beneficial from the point of view of beach width. All right, I talked about waves. I'm not going to dwell on this. I think this might be another of Doug's photos. He was up in an airplane in Santa Barbara during the February 1980 storm event, and you'll see a line of palm trees back here in a parking lot where the beach used to be out here. This is Ledbetter Beach in Santa Barbara. The edge of the beach used to be out here at the turn in the breakwater and filled all this up. And you see this, this was as if God woke up one February and decided, how can I wreck Santa Barbara? I'll send waves right down the channel, and they'll break and it'll mess everything up. And boy, it did some damage to the breakwater, and it ripped out this beach. So waves do flooding. They move sand both in the on-offshore and in the longshore direction. But of course, we need them very much for, as I said, one of the quintessential cultural attractions of California, and that is surfing. So in a very, very general sense, and I won't get into specifics, I'll show you a few pictures, but I won't get into much of the specifics of the wave complexity of the Southern California wave problem. But just remember that there are three general sources for waves. One is the Northern Hemisphere swell. In the summer, we have predominantly Southern Hemisphere swell. Well, duh, it's winter in the Southern Hemisphere. So these waves come generated from storms in the Southern Hemisphere and the South Pacific. They literally travel halfway around the world to break, and surfers, of course, love this because they have generally long periods, very clean shape because they've traveled for such a long distance. And the upshot is that in wintertime, the net transport of sand, because of the angle of approach of these waves, generally drives sand to the south. In the summertime, it's driven back to the north, only not to the same degree. So the general drift of sand on this coast is from north to south. There's also some local component due to local winds, local storms that make it right in here, so those are the seas. And the complexity arises because of the complex offshore bathymetry, again, directly related to the tectonic history and the geology, the geological history of the region, and the presence of these islands here, the Santa Barbara Channel Islands, Santa Catalina right here, and San Clemente right here. So these greatly complexify the situation. And I'm not going to dwell on this, but I just wanted to point you to the website where you can study this in great detail. There will be questions about this on the quiz that you'll take on your way out. Don't forget to pick that up because there's homework as well. Please, if you have a chance, look at CDIP, CDIP, Coastal Data Information Program, .ucsd.edu. It's almost as many as hamburgers served. We get hundreds of thousands of hits on a big day. This was 2002. Offshore wave heights were 19 feet. You see this is a color-coded wave height map. So you see 18 to 21 is this yellow color. And then you see the shadow of Catalina right here. You're in the dark blue, so you're 0 to 3 feet or 3 feet or so in the shadow of Catalina. So these shadows extend to the coast, as well as the complicated bathymetry underwater that didn't emerge yet to make islands, makes a very, very complex wave picture so that wave heights can vary by large factors in very short distances. South of Point Conception. So here's a map from Point Loma down here all the way up to Point Conception over here. So in general, the wave heights are much smaller in Southern California than they are north of Point Conception, just because of the orientation and the island sheltering that's involved. Please look at this model. This is modeling based on measurement. It updates once every hour. It covers the entire California coast. And it also runs in a 3-day swell forecast. I think Julie Thomas, the programmer that works on this, is in the audience. Any hard questions, you can refer to her. These are 3-day forecasts. As I said, these are based on the Navy's fleet numerical models that are updated regularly. Also, I think it's once a day these are updated. But the Navy spends a great deal of effort, keeping their carrier battle groups from having to steam through 40 or 50, I think these are 60-foot waves here on 48 feet. They don't want to drive into this, they want to drive around it. So they spend a lot of effort making these forecasts, and we use them to drive the coastal models. All right. Now, this is some new results that I just saw a few days ago, actually, courtesy of Bill OReilly, who's the chief scientist of the CDIP program, analyzing wave climate, at least for 1 year, and it'll probably hold up. What he's discovered, I mentioned the oceanside cell, right? Starts at Dana Point. This is Oceanside Harbor right here at about the middle of the cell. Dana Point would be up here. So he's looked at the oceanside cell from Oceanside south to La Jolla, and what he's discovered is that the waves have made a deal with the continental shelf bathymetry such that the longshore transport of sand goes to 0 at the lagoons. So this does a lot of explaining. What this suggests is that the Oceanside cell, at least south of Oceanside, can be thought of as a series of subcells. So at the southern end of each of these subcells, around the lagoons, just south of the lagoons, are erosion hotspots. And right at the lagoons is a tendency for sand to pile up because it's moving south faster toward the lagoon mouth than it is moving south away from the lagoon mouth. So it tends to pile up there. And this explains, or is one reason why we seem to have such difficulty keeping our lagoon mouths open. All right, if you follow, especially San Dieguito, this is undergoing a huge restoration now by Southern California Edison that just got started. But it's always a struggle. Penasquitos the same way, to keep these lagoon mouths open and fresh seawater flushing these things. There may be something, or there likely is something in the wave climate that conspires to do this. So what this means as far as the health of the beaches and the nourishment, future necessary nourishment of the beaches, is that local sand supply is crucial. It's not just so simple that you dump a whole ton of sand up here at Oceanside and then expect to see it down here some years later with all of the all of the intervening communities having partaken of the benefits of that. This system, at least with this scenario, if this holds up to be true, doesn't quite work in that very simplest of all conceptions of a literal cell, because it's divided up into these subcells. So this tells us something about how to engineer beach nourishment. In other words, you have to put some here, and you have to put some here, and you have to put some there as a strategy. All right, let's move along to climate. And this is a picture you can see in the newspaper, and in fact, if you've been looking at the newspaper over the last few weeks or even months, you'll see this high pressure system has been parked. Now, this is '97, but it was essentially the same picture over the last couple of weeks and months. This high pressure system is parked over the western United States, and what that does is, this is the jet stream right here. Here's a cold front approaching, a low pressure system with storms approaching, and the jet stream just steers this storm front up into Canada and Alaska, essentially where it belongs, right? And keeps us blocked. So meteorologists don't like when I talk about meteorology as much as geologists hate it when I talk about geology. But anyway, you can think of this as a blocking high. It's a high pressure system that essentially blocks the California coast from getting storms. Now, this was in December '97. It was actually an El Nino year, but also the height of a drought. Because there were storms in the Pacific, you see them. There's another one right behind this one, but they were all steered to the north, as they were a few weeks ago when we had all of this flooding up here in Seattle, you might recall, in the Pacific Northwest, and down here it was sunny and beautiful, and we were all going to the beach. And it was essentially because of this situation. Now, in February '98, this turned around. The high pressure system moves quite a ways south off of Baja. The low pressure, the Aleutian low, this thing right here, moves to the south also, and the door is essentially open to storms barreling across, essentially across the entire North Pacific, or storms generated in the Aleutians moving down the coast and making landfall directly in California. So this is one of my favorite quotes. It's from Robert Heinlein: "Climate is what you expect and weather is what you get." Weather, of course, is much more variable. Climate is a statistical average over a long period of time. But on any given day or any given month or any given year, it could be raining, it could be sunny, even though on average we have an ideal climate. But that doesn't mean it can't rain 6 or 8 inches in one day. All right? So the average position of these high and low pressure systems, relative position, is essentially what determines what kind of winter storm activity that we'll have in any given winter. Okay, so having said that, storminess varies on time scales of certainly seasons, obviously summer to winter, but it also varies on decadal time scales, 10, 20, 30, 40-year cycles that have been actually in the instrumental record. This is, I won't explain what all this is, but just take my word for it that if this statistic is going down, it's dry because you have lower than average rainfall every year. When this thing is going up, we have wet because it's higher than average rainfall every year. The instrumental rainfall records go back to the 1840s, but tree rings and other proxy records, deep ocean critters, what are they? Calcium? Sorry, who knows about that? Anybody know about this? Thank you, 4Ms, show that these kinds of climate cycles extend back probably thousands of years. Tree rings show it for at least hundreds of years. So these wet and dry cycles, usually the dry periods are longer, in this case from 1947 or so to 1978. This would be 1980 when it started raining again. So we had a 40-year dry period here, and of course this coincided with most of the development on the coast after World War II. So right after World War II, we went into this dry period starting about 1978, 1980, 1982, 83, 1997, 98 were these big El Nino winters. El Nino became a household word. During the early storm sessions, I actually heard one gentleman who had been living on the coast all his life say, "Boy, you know, I haven't seen it rain like this in 50 years. Well, yeah, that's right. You hadn't. Because the last time it rained that hard was, 1941 or so. So these climate cycles are very closely related to conditions in the Pacific Ocean. And I'm going to mention the word El Nino. I already did. I'm not going to go into a lot of detail. I just don't have the time to talk a lot about how El Nino works and what it does for us. But you can think of the kind of piling up of El Nino over the decades. El Nino is a phenomenon that occurs intermittently on years, 2 to 7 years, say. But this thing called the Pacific Decadal Oscillation, which is, I can't remember what it is, whatever it is. It has to do with pressure and temperature of the Pacific Ocean, surface waters. Has these dry periods where it's cold, relatively inactive, and then it has these El Nino-like episodes, decades where it's relatively wet. And you see from 1978 or so up until the present, over the last few years, I haven't put the statistics on here in the last few years, but presumably we're either still in this wet regime or we've now maybe crossed into another dry regime. We won't know for 30 years until it's over, essentially. Let's talk about sea level. Well, sea level, duh, what is it? It's ocean height relative to land. I've already talked about waves. Waves aren't usually considered sea level, but tides are. Storm surge certainly is. And then there's this whole suite of mean sea level, depending on how long you take the average. So there are seasonal changes which involve monthly averages. I'm not going to really talk about that. El Nino, I've already mentioned, interannual changes on 2 to 7 year time scales. Sea level during typical El Ninos is higher than it is during non-El Nino years by as much as a foot in some cases, extreme cases. There are dynamical effects. This has to do with changes in the gyre circulation of the Pacific Ocean, of course driven by large-scale wind patterns and large-scale atmospheric pressure patterns. This can lead to decadal scale changes in sea level at the coast in the centimeter to tens of centimeters, so good fractions of a foot range. And then, of course, the warming, global warming and melting. So warming expands the seawater. Warm water takes up more space. It's less dense than cold water. And then, of course, melting of land-bound snow and ice as the Earth warms puts more water into the ocean, fills it up, and the water level rises. This warming is especially important for warming of the deep ocean. The average depth of the ocean is about 4,000 meters, right? 4,000 meters, that's 4 kilometers, 2.5 miles or so. Only a very small fractional percentage expansion of that water column can lead to a substantial increase in sea level height. And of course, that's one of the things everybody's afraid of with global warming. As the ocean mixes very slowly and the bottom layers warm, then the ocean rises, in addition to the contribution from melting. It's thought that this is probably about 50-50. Half of it's from warming, due to global warming, and half of it's due to melting. All right, ice ages on the millennial time scale. This is thought to be driven, but not completely controlled, but at least the pacemaker for this are changes in the solar cycles on roughly 25, 40, and 100 and some thousand year cycles. So driven by very small changes in the amount of sun reaching the Earth, that sets the pace for these. And then we'll talk a little bit about what the future might hold. Now, the tides are important, as Sven over here discovered. See, they did some looting over here. Now they can't leave because the tides dropped and they can't get their boat off the thing. So it is important. I want to mention a few things. Tides are one of my favorite things to talk about. I want to mention a few facts about the San Diego tides. The tide range in the wintertime and in the summertime are bigger than they are, the maximum ranges are bigger than they are in the spring and in the autumn. The phasing is such that the higher high occurs and then the lower low, and then it takes the rest of the tidal day to go back up through the lower high, the higher low, back to the higher high. And you have to say that 10 times fast. Now, one of the interesting things that you may know about if you live on the coast is that during the wintertime, the higher high tides, in other words, these ones right up here, always occur in the morning. And that's loosely defined from midnight to noon. Whereas in the summer, the higher high tides always occur from noon to midnight, so in the afternoon. And this has a bunch of consequences, most notably for coastal preparedness. If the first time you hear about a storm impacting the coast, if you live on the coast, is on the 11 o'clock news, see, then you have a problem, because the storm waves and the storm itself occurring overnight and in the morning, coinciding with that high tide, that's when all of the damages and all of the destruction occur that we read about and know about. So knowing about the tides is, for, if only for that reason, important. It also has some consequences for the intertidal ecology that I won't go into. We can talk about that later. Now, one of the things we've discovered recently is that the tide range itself is increasing, and what that means is that the high tides keep getting a little bit higher every year. So you'll see from the San Francisco tide record that goes back to, this part started in 1900, actually goes back to 1850, but the analysis from 1900 shows that there's been about 1/4 of a foot per century increase in the high tides, along with all these 19-year fluctuations that has to do with some complicated motion of the moon. But anyway, besides those changes, you'll see that there's a trend in these highs, and this is 1/3 again as large as sea level rise itself. So if you think if you're worried about sea level rise, well, mean sea level doesn't flood you. Mean sea level doesn't run across your doorstep. It's the storms during the high tides that do. So if you thought you had a problem with mean sea level, well, your problem is actually 1/3 larger than you thought, because the tides are also increasing in height. Now, nobody knows if this is going to continue in the future, but there seems to be a pretty steady increase over the last 100 years, so there's no reason to think, especially, that this will stop. We don't exactly know what's causing this. We have some theories, but we don't exactly know what it is. So before we know what it is, it's hard to predict it into the future. I'm going to talk about a little bit about sea level in the past, namely over the last 18 or 20,000 years. And again, this is from a paper by Doug Inman and company. And there's some really interesting and I think telling and probably important points that I need to make. But let's look at the increase in sea level over the last 18,000 years. So we have about 120-meter increase over the last 18,000 years. And this is at the end of the last ice age. As the glaciers melted, the Earth warmed, sea level has come up, and it came up very rapidly up until about 8,000 years ago. So from here to here, from 16,000 to 8,000 years ago, the average rate, parts of it were much higher, twice as high even, and parts of it had still stands, very nice big fat still stand right here. But the average rate for that was about 125 centimeters per century. CY means century, 100 years, okay? Now, 6,000 to 5,000 years ago, we're in the neighborhood of what sea level rise is at the present time, and that's about 20 centimeters per century. About 5,000 years ago, Doug had 0 until the present time. I put about 1830 because there's evidence that sea level rise has accelerated in about, as early as 1830. So I'm going to call it 1830. From 5,000 years ago to about 1830, average sea level rise was about 4 centimeters essentially. That's essentially dead still. It's very, very, very slow. Now, what's interesting about this as far as the beaches are concerned, so I'm going to get to the beaches, I really will, is that it's been shown that beaches started to form, certainly in the oceanside cell and probably in the rest of Southern California, about 5,000 years ago. So you see these dates here, 7,500, 4,870, 4,090. So about 5,000 years ago, you see the increase in the yellow, that's sandy shoreline, and relative decrease in the rocky. So that's the non-sandy shoreline. So prior to that 5,000 years ago, sea level rise presumably was going up at a rate too large for beaches to form. Now, as I said before, this is also intimately related to the sand supply, but everything else being equal, the sea level rise itself was probably too large prior to this time for beaches to form. Well, as I said, we are now since the last century in a range of sea level rise that equals approximately 20 to 30 centimeters per century. So now we are back up to this rate of rise before the beaches were able to form. Now, I can't tell you, I don't think anybody can tell you whether that means, everything else being equal, that the beaches will disappear, but it certainly is suggestive. So as I indicated in the previous picture, sea level rise has been going on for a while. What's new now is that there's acceleration of sea level rise that has been documented for the first time over the last 5 years. Here's some numbers that have been compiled. From 1930 to 1990, we have this background rate of about 18 centimeters per century. Satellite data and other proxy records now, and tide gauge records themselves, suggest that this has accelerated 25 up until 2001 to 29 centimeters a century, and this is the newest information from 1995 to 2005, we're at a rate of about 32 centimeters per century. Now, these times, 10 years, this is too short to have good statistical significance in the trends as far as projecting 100 years into the future, but there certainly is now evidence, and you can see it in the picture. You can see it in the picture here. Up until about 1830, there's 1830. Statistically, it's been shown that it's now known that there was an acceleration. There's a documented acceleration as measured by the tide gauge. There's some very long tide gauge records back to 1700 at Amsterdam in France. And this is actually the German pronunciation is Swinemünde. That's a little easier. It's in Poland somewhere. Same kind of picture. And San Francisco, again, back to 1850, similar sorts of pictures. So what are these fools doing? They're looking into the future. And what might we see? What might we see in a warmer future? Well, in the warmer future, various climate scenarios, and I won't get into all of the details of this, obviously, but these are different climate scenarios that are run depending on aerosols, depending on CO2 uptake, depending on fossil fuel burning, depending on if you had a birthday party and you drove the Mercedes or the Bentley, for CO2 emissions, depending on a whole host of things, there are different future scenarios. These are not predictions, these are scenarios. I want to emphasize that. No scientist in his right mind or even in his wrong mind would say that these are confidence, sort of predictions that you can make with any confidence. These are scenarios. If certain things happen, then this is the warming we might expect. So over the next 100 years, here we are in 2000 and some, up to 2100, we might expect a 2-degree to a 5-degree warming. So what does that mean as far as average global temperature? It doesn't sound like much. I mean, you walk outside, it's going to be 20 degrees colder. Well, 10 degrees centigrade. So it doesn't sound like much, but you have to look at this picture of the temperature of the Earth in the last 5.5 million years to see, here we are at present, right, at 0. Present is over here on the left. 5.5 million years ago, we've been cooling, according to this data. The warmest it's been in the last 5.5 million years is about 2 degrees warmer than it is now. 2 degrees. Well, 2 degrees is kind of the minimum we expect over the next 100 years. Now, about 2 million years ago, we went into these ice age cycles. That's what these are. And you see, when it's cold, we have glaciers, and when it's well, the other way around. When it's cold, we have glaciers, and when it's warm, we don't. We have interglacials like we do at the present time. And the difference in average global temperature between these height of the glacial, right, you know, where there's 2 miles of ice covering Manhattan, the difference in global temperature is only a few degrees, you know, 3, 4, 5, 6 degrees. So what this suggests is that if we go beyond 2 degrees in the next 100 years of warming, we will be out of the range that the Earth's temperature has been in the last 5.5 million years. And we are truly, in that sense, in uncharted water, uncharted territory. Now, you know, this is, these are some of the more outlandish scenarios. Those are the kind of normal carbon dioxide buildup global warming scenarios, normal, not projections, but scenarios. There are some another set of truly scary scenarios that involve a large-scale melting of Greenland. That's the one on the right, where it's been now documented that the Greenland Ice Sheet is thinning at an alarming rate. And the granddaddy of all, well, if that whole thing melts, we might see 3 meters, so 10 feet. I can just step out of my office and basically, you know, be in the water. The graduate students in the basement will need snorkels. The really scary scenario, a collapse of the West Antarctic ice sheet, shown over here on the left, and in schematic form on that picture on the upper left. That's the really scary scenario. That involves 6 meters. Now, the time scale here is a little uncertain. At least I don't know what it is. It might be, it's certainly more than decades. It's probably centuries. Nevertheless, 3 meters or 6 meters increase in sea level over even a few centuries is a very serious thing. But these are not expected. They are very, very unlikely events. But they are also, of course, relatively, you know, proportionately serious and catastrophic events. So what do we have here? Well, we have some scenarios for future sea level rise, and I've chosen the medium ones, 50 centimeters. And if you'll bear with me here, I want to show you what might happen with a 50 centimeter rise in sea level. And what's going on here is that this is a commonly used picture to show what happens when you build a seawall. This could be a cliff also for high rates of sea level rise. You could have a cliff back there. So in the upper picture, you see you have a nice wide beach where it says beach width. If the sand disappears or if sea level rises, the beach can't retreat back because of the seawall or the cliff if it's rising fast enough. And so what that results in beach loss. You see the narrowing of the beach where it says beach loss in the bottom picture. Well, for moderate rates of sea level rise, you fix this with money. All right, so you find some money and you rent the dredge. He gobbles up the money and he lays a pipe to the beach and he pumps some sand. You probably have cost overruns, so you have to find some more money. But then you essentially put the beach back by pumping sand, and that's for moderate sea level rise rates. That's a viable option. Now, what kind of volumes are we talking about? Don't take these scales here seriously. This is clearly not to scale and out of proportion. But let's just say nominal values, a thickness of 50 centimeters, that's to make up for that 50 centimeters of sea level rise. You have to spread that. Remember, we looked at those profiles earlier, from a height of 2 meters out to a depth of 10 meters. That's 12 meters total. If the beach slope is 1 in 100, that gives you a 1,200 meter beach width that you have to cover. And here's some arithmetic. That means, and I remember to ask you to remember those numbers, 600 cubic meters per meter will make up for that 50 centimeter sea level rise. If your beach slope's a little steeper, then it's a little cheaper. If the sea level rise is less than a half a meter, then it's a little cheaper. The total volume, just estimated for California, 425 kilometers. If 3/4, they're 0.75 of the length is beach. That amounts to about 2 million cubic yards per year you can keep up with sea level rise at that rate. So that, if it's $5 or $10 a yard or meter, that's 10 million to 20 million a year. Now, to me, that's a lot of money. To you, well, some of you it might not be, but for most people, that's a lot of money. But let's compare that with some other monies. We can compare it, for example, with the several billion dollars with a B that California collects in taxes due to directly related coastal tourism and recreation. So that's one thing we can compare it to. I asked you, remember those numbers between 500 and 1,600 cubic meters per meter earlier. So in terms of the seasonal cycles that we see, in big winters, it's not really that big a number. So for very large sea level rise, though, of course, then it just drowns the whole thing, and it'll be impractical and uneconomical to keep up. And what we'll have is what Doug calls a plunging cliff platform, or a plunging cliff. I call it a fjord-type coastline, where the beaches are essentially drowned. We have some examples of that, so it's not totally unknown what that might look like. The upper picture is part of La Jolla, Point La Jolla, which is essentially that drowned plunging cliff landform. And the bottom one is Point Loma, clearly same thing. There's relatively little beach, if any beach. The waves break right on the cliff most of the time. So we'll probably see much more of that if we have some of these much larger rates of sea level rise. Now, the seawall debate, well, in my view, and I think most would agree, under the present law and policies, seawall proliferation, and again, not just for private property, but for public infrastructure. I've got a bunch of pictures here you can look at yourself. I believe is inevitable. I think it's very sad. I also think the way we've chosen to develop the coast, it's also necessary from that point of view, at least in some sense. Now, having said all of that gloom and doom and not being very optimistic, I'd like to read you my favorite poem. And now, if this is literally true, if he was here, if Robert Frost was here once by the Pacific, I've been here 38 years, it's taken me this long to learn all of this stuff that I've tried to summarize tonight. If he did this in one day, it's just really amazing. Anyway, he says, the shattered water made a misty din. Great waves looked at others coming in. So there's the waves. And thought of doing something to the shore that water never did to land before. So a little bit erotic there also. The clouds were low and hairy in the skies, and there's your storms, like blocks blown forward in the gleam of eyes. I have no clue what that means. You could not tell, and yet it looked as if the shore was lucky in being backed by cliffs. So there's the geology. The cliff is being backed by continent. There's continental drift and plate tectonics. It looked as if a night of dark intent was coming, and not only a night, an age. So he knew about the ice ages and the climate cycles. Someone had better be prepared for rage. And he's talking about Coastal Commission applicants there. There would be more than ocean water broken before God's last put out the light was spoken. Thank you very much.